Pluto is a remote and faint, more modest celestial body that was formerly a component of our local star system. Nevertheless, recent and startling statements by prominent space scientists Neil deGrasse Tyson and Michio Kaku have returned Pluto to public attention. They proposed that this faraway object might be on a probable collision trajectory with Neptune. They're not just speculating, they're warning this tiny world could be on a dangerous, direct path toward a catastrophic collision with Neptune. But how could that possibly happen, and what would the consequences be if such a titanic event actually occurred? Are we witnessing some kind of bizarre cosmic illusion, or is something far more real and far more terrifying hurtling toward us? Pluto's orbit cuts alarmingly close to Neptune's. Neil deGrasse Tyson and Michio Kaku are sounding the alarm. If things shift even slightly, we could be looking at a disastrous planetary mishap. Could Earth be in danger too? And more importantly, how is such a cosmic event even possible? Accompany us as we explore the potential ramifications of a Pluto-Neptune impact. Pluto, a former planet that was reclassified as a dwarf planet, continues to be a topic of fascination in the expansive cosmos, as illustrated by current theories. From top-tier analysts, Pluto's trajectory is dangerously close to Neptune's. Space experts Neil deGrasse Tyson and Michio Kaku are both sounding the warning about a conceivable hazardous interaction between these two worlds, which might suggest a tremendous risk to Earth. Still, how might such a scenario be achievable? Pluto's voyage around the solar star is unlike that of any other celestial sphere in our planetary system. It takes an astonishing 248 Earth years to finish a full loop. Since its identification in 1930, it has yet to complete even one complete cycle. However, the curiosity doesn't end there. Pluto's trajectory is defined by its exceptionally elongated path, deviating significantly from the mostly circular revolutions of the principal planets. What makes Pluto's path even more extraordinary is its tilt, which is 17 degrees from the solar plane. The route Pluto traces is significantly more irregular in contrast with other planets. This tilt and eccentricity add layers of complexity to its orbital pattern. Arguably, one of the most intriguing elements of Pluto's orbit is its overlap with Neptune's. For approximately 2 decades during each circuit, Pluto actually becomes nearer to the Sun than Neptune, contrary to what one might expect based on their conventional planetary placements. This brings up the standard question, why hasn't Pluto collided with Neptune? The explanation resides in the gravitational influences of surrounding planetary bodies. The examination of Pluto's trajectory began shortly following its revelation. Initially, astronomical researchers attempted to comprehend its distinct route. Unlike most other planets, whose loops are relatively aligned with the solar plane, Pluto's route stands out with its sharp angle and uneven layout. The enigma deepened with the understanding that Pluto's orbit does indeed intersect Neptune's. The steadiness of Pluto's path, despite these irregularities, stands as evidence of the subtleties of cosmic physics. The three-body dilemma in outer space entails figuring out how a trio of cosmic entities, like Pluto, Neptune, and the Sun, move and affect each other through their gravitational pull. It's akin to forecasting future movements based on original positions and mutual gravitational tugs. In Pluto's case, this issue highlights how its motion, Neptune's loop, and the Sun's pull all operate in an interwoven way. The expressions asynchronous oscillation, orbital drift, and VZK wobble are essential to unraveling this puzzle, as noted by astrophysics specialists. What maintains the planetary bodies in their circular tracks is asynchronous oscillation. Regarding Pluto and Neptune, this phrase fundamentally means that when Pluto passes through Neptune's orbital path, it is situated at no less than a 90 degrees angular distance away from Neptune. This angular separation is vital in preventing their paths from clashing. Orbital drift, by contrast, refers to the vertical motion of a body as it revolves. For Pluto, This indicates that when it gets closest to Neptune or another giant world, it lies significantly above their orbital tracks, providing an added level of defense against likely crashes. An additional major component in this discussion is the VZK wobble, named for three researchers, Zell, Kai, and Kaku, who analyzed the spatial dynamics of cosmic entities. It involves how three astronomical masses, like Pluto, Neptune, and the Sun, exert pull on one another with their mass-based attraction. This influence shapes their movement. In Pluto's instance, the VZK wobble provides insight into why its route near the Sun appears so erratic. Although Pluto's movement seems unstable, this wobble aids in keeping it flowing smoothly across vast durations. The VZK wobble reveals that even though the cosmos may look chaotic and strange, principles and patterns still enforce some degree of order. These dynamics assist in sustaining Pluto's steady path, making sure it doesn't crash into Neptune or stray from its regular route. This tri-body interaction is crucial to grasping how space trajectories shift due to interjecting forces. Analyzing it teaches us more about Pluto, our planetary group, and even far-off galaxies and their stars. Numerical projections in the late 1980s demonstrated that, even though Pluto's orbit is reinforced by stabilizing attributes, it remains erratic. Small initial variances can produce dramatic divergences over centuries. Still, these orbital behaviors have been proven to maintain equilibrium over astonishingly extensive timelines. Evaluating changes via later automated readings has helped us learn how the behemoth planets, Neptune, Jupiter, and Saturn, affect Pluto's revolution around the Sun. Neptune shares a distinct orbital correlation with Pluto, in which, for every 2 revolutions Pluto performs, Neptune finishes 3. This synchronized relationship helps preserve Pluto's stability. However, Neptune doesn't act alone. Jupiter's immense gravity contributes heavily to keeping Pluto's track consistent. Saturn, as well, adds to the mix. Research reveals that Jupiter's colossal mass is powerful enough to secure Pluto's course for potentially an extremely long duration. It seems that Neptune, Jupiter, and Saturn are all working in harmony to guarantee that Pluto glides securely through the void without encountering hazards. These strange yet essential systems play a major role in maintaining cosmic order. Without such mechanics, our solar neighborhood would be a far more turbulent realm. Objects like Pluto might collide with others or be ejected entirely, causing domino effects with other astronomical entities, especially concerning Pluto and worries about its future interactions with Neptune. Understanding its motion is key. This offers a sharper image of the vibrant and ever-shifting nature of our planetary cluster. Pluto's example illustrates how even seemingly unstable paths can reach balance via intricate gravitational and kinetic interactions. It also underscores the necessity for continuous monitoring and scrutiny of such oddities to better comprehend our place in the cosmos. Probing deep into outer realms often makes us confront the bizarre characteristics of heavenly bodies. Furthermore, Pluto's orbit is a perfect case of this irregularity. The theory of orbital disorder, which denotes the sensitive dependence of an orbit on starting data, is clearly visible here. For Pluto, this suggests that minimal alterations in its coordinates or speed could greatly influence its far future pathway. Utilizing computer-based forecasting has proved extremely beneficial for space scholars working to decode Pluto's behavior. These programs employ elaborate equations to simulate how Pluto and other bodies like Neptune interact gravitationally. By adjusting minor aspects within these forecasts, scientists can observe how even slight shifts can lead to completely altered destinations. In the late 1980s, these digital models revealed a surprising trait about Pluto. Though it has stabilizing mechanisms like asynchronous oscillation and orbital drift, its journey may still behave abnormally. If Pluto begins with just a tiny discrepancy in location or velocity, its future position might look vastly different in only a few years. Yet, despite this unpredictability, Pluto's trajectory has endured across immense spans of time, spanning billions of years. That means Pluto's path has an underlying consistency, despite seeming unruly at first glance. Predicting stellar orbits, particularly ones as inconsistent as Pluto's, remains a monumental task. The core unpredictability of such systems makes far future predictions riddled with unknowns. Although models built on math are outstanding for decoding and estimating cosmic motion, they also highlight our limits. These formulas depend heavily on starting values, and even a minor inaccuracy or alteration can shift the result dramatically, making pinpoint precision a true challenge. Beyond the erratic tendencies of planetary pathways, Pluto highlights the constant evolution and flux of the universe. Although humanity has uncovered significant knowledge about the stars, Pluto's oddities remind us how much still lies in the shadows. Deciphering how massive planets alter Pluto's movements grants us broader awareness of solar system behavior. It shows how each planet's presence and place can meaningfully influence the steadiness and direction of others within the structure. So, why are notable astrophysicists suddenly expressing anxiety about a possible smash-up between Pluto and Neptune, even with all the cosmic laws acting to prevent it? Neil deGrasse Tyson, a well-known space scholar and a key promoter of cosmic knowledge, delivers a distinct angle on our planetary mysteries, especially Pluto's peculiar saga. Tyson, recognized for his efforts in demoting Pluto to dwarf status, provides perceptive thoughts on the shifting principles of orbital science and the public's curiosity in the overlooked regions of the heavens. His stance on Pluto's label change stems from our constantly improving understanding of the solar neighborhood. He views the shift not as an insult, but as a critical correction to our grasp of objects revolving around our star. Tyson's outlook on orbital physics emphasizes continual education and flexibility. He interprets complicated trajectories like Pluto's as a symbol of how much more there is to uncover. The mystery of such questions keeps astronomy thrilling. However, while Tyson remains hopeful, his outlook on a potential Pluto-Neptune collision is far less cheerful. His apprehension about Pluto's destiny, once a full-fledged planet, is rooted in his recognition of the erratic behavior of these orbital dances. He admits that, while Pluto has thus far remained secure, small changes accumulating over time might trigger disastrous events. Pluto's trajectory, particularly its overlapping zone with Neptune, forms a complex spatial rhythm that may not remain in sync forever. In Tyson's perspective, even the slightest disturbances in Pluto's path could yield huge consequences. If these imbalances grow over millennia, they could eventually result in chaos or even a planetary crash. But such a development wouldn't happen in the near future. Instead, it would span unimaginable lengths of time, well beyond the reach of human civilization. Still, Tyson's cautious tone calls for further vigilance and deepened investigation into Pluto's orbital pattern. Tyson isn't standing alone. Michio Kaku, a renowned theoretical physicist, also perceives the astronomical upheaval that might result from interplanetary interactions. Although Kaku matches Tyson's awe for the grandeur of the universe, he too recognizes the shaky balance of planetary orbits and the wild, unforeseen effects that may arise with time. Both Kaku and Tyson highlight the necessity of persistent space exploration into the invisible powers dictating planetary drift and the outlook for our starbound family. In the end, Pluto's situation exemplifies how our understanding of the universe is fluid, always adjusting. Each breakthrough leads to further intrigue. As space science progresses, the slim possibility of a Pluto-Neptune collision is a humbling reminder. Outer space is filled with unexpected turns, and even peaceful planetary paths can change drastically over time. These lessons from Pluto serve to remind us to keep watching the skies and keep wondering about the secrets that the stars still hold.